Okay, let's start. So we were discussing shortest path, all path shortest path problem. So the question is, we are given a graph, two vertices S and T. So in fact, this is the single source shortest path problem, where you are given a single vertex S, and you want to find the shortest path length to every other vertex. Okay. And we want to solve this by the greedy approach. So we are discussing Dijkstra's algorithm. So I'll just recap what we did last time. So if you are given this graph G, consists of vertices and a set of edges. There is a weight assigned to every edge. So every edge UV gets some weight WUV, right? And there is some source vertex S, and we want to find the shortest weight path from S to every other vertex. And so we want to store this shortest path length in some array T. Okay, it is indexed by the vertices in the graph. And what we did was we set D of S to be 0, and for every other vertex it's initially set to infinity. And we will change these values so that they finally converge on the exact shortest path weight. And this algorithm, not only does it give the shortest path length, but it also returns that particular path. So that is why we had this parent, sort of parent pointer, which is the vertex preceding the B in the path. Okay. Okay. So the way we did this, initialize some priority queue. Okay. It depends on whatever data structure you want to use, and initially S is set to empty set, and we will slowly add vertices to these sets such that it will only include those vertices whose shortest path length we already know. Okay. So what we did was initially we set this queue to contain all possible vertices, and then we extracted minimum D value uh, out of these vertices. So that is the extract min operation. Okay. For different data structure, you have different time complexity for this extract min operation. and we added this minimum to the our set. Okay, correctness we'll analyze later, but this set will always consist of those vertices whose shortest path length we already know. So in this case, we set distance of S to 0. So what is the shortest path length from S to S? It is 0 length. You don't have to traverse any edges. Okay, and we keep on doing this. And how do we update this DV? So there might be a finite length path. So this is initially set to infinity. So we want to reduce this infinity value to some finite value. And for that, we use this relaxation step. Okay. So what is our relaxation step? For every neighbor of U, if let V be a neighbor of U, if dV is larger than du plus WUV, right? So what is du plus WUV? We just first go from S to U and then traverse the edge from U to V. Okay. And let's say our initial D value is larger than this, then we set dV to du plus WU. Because we know a shorter path than the initial D value, this is that path. We go from S to U and then traverse the edge from U to V. And in this case, the vertex immediately preceding V in this path is U. So we set the parent of V to U. That will help us output the actual path, not just the shortest path length, but the actual path. Okay. And this is the decrease key operation, right? We are decreasing dV to its initial value to this particular value. Okay. So there are only two operations here mainly, which is the extract min and decrease. Okay. So we'll analyze the running time later, but first we want to analyze the correctness of this algorithm. Why does this procedure work? Okay. And that is the more difficult part in greedy algorithms. Strategy, everybody can think by themselves, but how to prove that your chosen strategy is correct? Okay. So initially what we did was we set ds to 0 and all other vertices are set to infinity. And then we slowly decrease the value by using this decrease key operation. And first we want to maintain this invariant that this dV will always be greater than or equal to the shortest path length from S to V. Okay. And how do we prove this? The usual way is via contradiction. Okay. Suppose not. For some vertex, dV is less than this delta S. Okay. So use some kind of ordering. So let V be the first vertex for which dV is less than delta SV. And obviously this dV, what's the current value is, it got because of some kind of relaxation step. So let U be the vertex such that dV equal to du plus WUV. Okay. And we know that dV is less than delta S. Okay. And the usual way to prove this in shortest path problems is via this triangle inequality. So delta SV is the shortest length path from S to V, and it is always less than equal to shortest path from S to U and then the shortest path from U to V. Okay, because this is one particular path and its length will always be larger than the shortest path from S to. It doesn't necessarily have to go through U. So this is the triangle inequality, and what is the delta UV? It is just the weight of the edge from U2. Okay. And Since we assume that V is the first vertex for which dV is less than delta SV, so we'll assume that all other vertices which are having this du equal to delta SV. Okay. So this delta SU, you can replace it as du, and this just remains plus WU. Okay. And since we started with a less than sign and all these subsequent inequalities are less than or equal to, then we have a contradiction that dV is less than du plus WUV, and we are done. Okay? Because initially we assumed that dV equal to du plus WU, so it's a straightforward proof. Okay, so then we have this lemma, which is that dV is always greater than equal to delta SV, and this invariant is always maintained over any sequence of relaxation steps. Okay, so once we have this, now we need to analyze the relaxation step. So we know that this condition is always satisfied, and let U be V's predecessor on the shortest path from S to V. So U is the vertex immediately preceding V on the shortest path. Then if du equal to delta SU and the edge UV is relaxed, now we want to show that dV equal to delta S. We already know that this is greater than equal to, but now we want to show that after this edge is relaxed, it is exactly equal to the length of the shortest. Okay. So again, we have this delta SV equal to, so since U is the predecessor of V on this shortest path, so the length of the shortest path from S to V is the length of the shortest path from S to U, and then we just follow this edge from U to V. Again, we use contradiction, which is suppose that dV is larger than this delta SV before the relaxation step. Okay, so dV is greater than delta SV, which is equal to this particular value. Okay, and what we also know that delta SU is equal to D plus WU. Okay. So this is before the relaxation step. dV is greater than du plus WUV. And after we relax this edge, we will get dV equal to du plus WUV. Okay. Which is just the length of the shortest path from S to V. We go from S to U and then traverse this edge from U to V. Okay. So this is assuming these conditions that it du equal to delta SU and so on. So finally, we would like to say that Dijkstra's algorithm always terminates with dV equal to delta S. Okay. So it's just sufficient to prove that dV equal to delta SV for every V when V is added to S. Okay. Again, we go via contradiction, which is that let U be the first vertex added to S for which du is greater than delta SU. Because if it is not equal, we already know that du is always greater than equal to delta SU, that is from lemma 1. So let's assume that U be the first vertex added to S for which du is greater than delta SU. Okay. Now suppose that we have this path from S to U. It's going through some vertices in S and some vertices V minus S coming back to S and finally reaching U. So you would let Y to be the first vertex which is outside S. Okay, and X is its predecessor which is inside S. know that the distance to x is delta Sx. Okay. And when y was added to s, because this is just assuming by induction, okay, that all the vertices inside s, we know their shortest paths. And when y was added to s, this edge was relaxed. Okay. And this will imply that dy equal to this shortest path from S to Y, which is always less than equal to the shortest path from S to. Okay, this is assuming the second lemma, which we proved above. Okay, and this is always less than du. Okay, so we get one inequality, which is that dy is always less than du. But what we assumed was, let y be the first vertex in V minus S along a shortest path from S to U. Okay. So du is less than equal to dy by our choice of u. Okay. So u was the first vertex added to S for which this particular inequality holds. And just combine these two things. Here we got that dy is less than du, but here we got that du is less than equal to d. And combining these two things, you get a contradiction. Okay. And yeah, so you just come up with some greedy strategy, and usually these correctness proofs are difficult, and that's the main challenge in this greedy part. Okay, and okay, this correctness proofs, and just analyze the running time of this. So we had n extract minimum operations, and where n is the number of vertices, m is the number of edges, there are m decrease key operations. So let me just go to this particular pseudocode. Okay. So this happened, we go of n times the extract minimum operation and this decrease key, because we took v belonging to whichever were adjacent to u. So this will at most be the number of edges. Okay, so there are m decrease key operations, n extract min operations. Okay, so what's the data structure we want to use to minimize the total running time? So there are many options which you can try, and let me show you the running time, which is either you take an array. Okay, so there is an array which stores these d values. Okay, for that extract min is obviously big O of b. Okay, you can't do better than big O of b in this case. And because array supports random access to any of its elements, decrease speed just takes constant time. Okay. Yeah, that's our priority queue. Okay. And you just combine these things. So n into extract min will take v square time, and m will just be the number of edges. Okay. So v square always dominates the total number of edges. The total running time will be v square. Other option is you use binary heap. All of you know what a binary heap is, and in that case, both extract min and decrease key, they are just log v time. Okay? And look at your data structure notes to see how this works. And so what's the total running time here? This is d log v. This is e log v. Okay? and the number of edges usually dominates the number of vertices, so the total running time will be E log. Okay. And this is in fact the best case for a deterministic running time, but if you allow amortization, we have a better option, which is this Fibonacci heap. And it gives extract min in log way time and constant time decrease key, and the total running time is E plus V log. Okay, so slightly better than this particular uh, algorithm, and particularly if the number of, yeah, this is actually better than running time. Okay. Okay, any questions so far? Okay, if there are none, that concludes our coverage of greedy algorithms. Okay. And in the mid-sem anyways, we are just covering up to greedy things. Okay. So what I teach next is not included in the mid-semester. Okay. So what have you seen so far? You have seen two different algorithm design techniques. One was divide and conquer. Okay. Divide the problem into various sub-problems, solve each sub-problem, and then combine the solution to the sub-problems. Okay. This was one thing. And the other was greedy approach, which is we make. So what is an algorithm? It's basically you need to make certain choices at every step, and the real challenge is how to make the choices. Okay? Takes decision by, and greedy what it does is it makes the locally best choice, and we hope that by making a sequence of these locally best choices, we will get a globally optimal solution. And once we have made these decisions, we don't go back and change it again and again. So it works only for a specific kind of problems, shortest path, minimum spanning tree, and certain scheduling problems. Now, the third thing we want to look at is this very nice tool called dynamic programming. Okay. So in the initial divide and conquer, I was telling you like you are not allowed to use extra space and just try to figure out what you can do without using extra space. So the only drawback of dynamic programming is it uses extra space, but usually you will get faster solutions than greedy and divide and conquer. Okay. But it also has its limitations in that uh, you can only apply it to problems where certain sub-problems are overlapping. Okay. Sort of like divide and conquer, but the sub-problems are overlapping. So you need to compute them again and again. Okay. And then we combine the solutions with sub-problems to give the solution to the large problem. Okay. So it's sort of like you have a difficult problem to solve, and so you make certain guesses at every step, and you just try all possible guesses. Okay. And those will give rise to sub-problems, and then you want to utilize the solution to the sub-problems to give the solution to your large problem. And we will see many examples to apply this technique of dynamic programming. Yeah, it is still shortest path. This is not included in your mid-semester. So what is the intuition behind dynamic programming? Okay. Uh, so okay. So it usually gives a polynomial time solution for certain seemingly exponential time algorithms. Okay. So there are certain problems that no matter how cleverly you divide and conquer or how cleverly you use your greedy strategy, you will always get exponential time algorithms. And the main problem is that you need to compute the solution to certain subproblems many times, which is giving rise to these exponential time algorithms. And so this is a method for solving optimization problems. We compute the solutions to the subproblems once and store these solutions in some table or dictionary or hash table or an array. So you can reuse them and you don't have to compute the solutions again and again. So obviously you need some extra space to store the solutions in table or hash table. But yeah, it is okay. But you get much better running time at the cost of extra. Okay. And the general outline of a DP solution is that you need to guess certain things, guess a part of the solution, and try all possible guesses. Okay. So we characterize the structure of an optimal solution by showing that it can be decomposed into optimal subproblems and recursively define the value of that optimal solution by using the optimal solution for the smaller subproblems. Okay. And the thing is that we don't know how to solve the initial hard problem. So we decompose into many subproblems and use these solutions to subproblems is to find the optimal solution. Okay. Then we compute the value of this optimal solution. Okay. And there are two ways to do it, which is top-down approach with memoization. So this is we memorize the solution to certain subproblems by storing it in an array. And there's another technique where we use a table and the bottom-up approach. So the only difference between that is space efficient. This bottom-up approach, space efficient. So you'll only need to use some constant amount of space using this approach, and top-down is more space consuming. Might need linear amount of space. Okay. And we want to construct an optimum solution from the computed information. Okay, so this was a brief introduction to what dynamic programming is, and I'll just change the. Yeah, okay. So here is our first problem in dynamic programming is that you are given this rod of length n units and there is a table of prices. So different length rods will have different prices, and it's not like rod of length 3 has thrice the price of length 1 rod. So there are different prices here. So for instance, here is a table. Okay. And what you want is that you want to cut this rod at certain points so that you can get the maximum revenue out of it. Okay. And the question is, how are we going to do? So let's say we have a length 10 rod, rod of length 1 has this price, rod of length 2 has this price, and so on. So let me just show, let's say there is some small rod. Okay, there is a rod of length 4. And how can we cut and sell this rod to maximize the revenue we can get? Okay. So what are the different ways to cut this rod? Okay. Either we don't cut it at any point. So this is a rod of length 4 and the total cost is 9. Otherwise, we can cut it into two pieces, one of length 3, one of length 1, and we just add the two revenues, 8 plus 1, again 9. Otherwise, two pieces, one of length 2, other also of length 2. Okay. And what we get here is that 5 plus 5. So it's 10. Okay. Another approach is length 1 plus length 3. Okay. So you get 1 plus 1. Okay. You can also cut the rod into 3 pieces or 4 pieces and you'll get these kind of revenues. And we want the maximum revenue. Okay. So how many ways are there to cut this rod into various pieces? Any suggestions?
2 raised to n minus 1.
Yeah, 2 raised to n minus 1. That's exactly correct. So how do you find 2 raised to n minus 1 is that there are n minus 1 choices to cut this particular rod. Okay, because even if you cut into length 1 each, and either you cut at that point or you don't cut. There are two choices for that, and get this 2 raised to n minus 1. Okay, so basic what you call counting. So this is a bad algorithm when we consider all possible ways to cut this rod and we would like to uh, compare their costs. So it's an exponential time algorithm. So then how do we find the maximum revenue? Okay. Can we do better than this solution? So any ideas how we can get polynomial time here? So notice that whatever we have seen so far, greedy and divide and conquer, neither of those works here. Because how are you going to divide here? So let me tell you one more approach of trying to do this better is that we can compute this maximum revenue in terms of optimal revenue for shorter length rods. Okay. So it's sort of like divide and conquer, but again it will give us exponential time. Okay. So let's say we just divide the rod into two pieces. Okay. And then we recursively compute the solution for each of these pieces. Okay. So first case is either we don't cut the rod at all, or we divide into two cases, 1 and n minus 1, 2 and n minus 2, n minus 1 and 1. And then both of these pieces we will further cut so as to get the maximum revenue. And that's what we store here, Rn minus 1, Rn minus 2, and so on. Okay, so Pn is if we do not cut the rod and if we take the sum of the optimal revenues for length 1 and n minus 1. Okay, so you can cut the rod into many pieces, but we are sort of adding up those things and writing it as a sum of two different things. Okay, so you can always write it as a sum of optimal revenues where one part has length I and the other part has length n minus. Okay, so this is what I'm trying to do, making an initial cut into two pieces and then further cut those two parts again. But we don't know which I and which n minus I we should pick here. Okay, so that's what we have to guess. So as I said, dynamic programming is about guessing and then consider all possible guesses. Okay, so I could be any value from 1 to n, and then we try to pick the maximum. Okay, so this is the way. Let's say there is a 20 length rod. We divide it into two pieces of length 8 and 12, and then further cut this length 8 rod and cut this 12 length rod. And so this optimal value we are already storing somewhere. Okay. So it has this optimal substructure property that optimal solution for some small part is always included in the optimal solution for the large. Okay. So to solve the original problem, we solve smaller subproblems of same type but smaller sizes. And once we make the first cut, again we consider those two pieces as independent instances of the same problem. Okay. So that's what we generally do, that if the initial problem is hard to see, and then just consider some special cases and try to use the solution of those special cases to solve the entire problem. And in fact, this is the only thing which works for all cases. Okay, so if you can't think of anything better, divide and conquer or greedy, let's say you don't have that divine intuition to make things work, you can always use this kind of general dynamic programming strategy, which is divide those problems into several smaller sub problems and then utilize those solutions. Okay. Or you try to guess a part of the solution and consider all possible guesses for that thing. Okay. So first let's look at this particular thing. What's the running time of this algorithm? Any suggestions? Is this a good algorithm? So you understand what's happening here, right? So every time we are dividing into two different subproblems of different lengths, and there is one thing where you divide it in the center, Rn by 2 plus Rn by 2. Okay? So again, you can write the recursion is Tn is always greater than equal to 2 Tn by 2 plus some constant number of additions and constant number of maximum. Okay, so again it's exponential because you need to solve these two subproblems, which are roughly one of them is almost equal to this R. Okay. So you can easily construct the recursion for this step. And so do we really need to uh, calculate these two subproblems of different length? Maybe if we can reduce to one subproblem, then we will be good. So any ideas how we can reduce this to computing the solution to just one sub? Okay, it's not too difficult to see actually. So the idea is that the first cut you have to make somewhere, right? And then we further cut this into further pieces. Okay. So let's say we made the first cut at this length I. Okay. And then we will have to pick all of these pi and then make further cuts into this remaining n minus I part. Okay. So a simpler equation is if you have a rod of length 0, obviously it's 0. And if you have a rod of length n, we make the first cut at length I and collect this price of length I plus Rn minus I. These cuts we still need to determine. Okay. So R1 is just going to be Pi plus R1 minus I. Okay. It's just P1 plus R not. So some simpler subproblems we can easily figure out. And obviously it will give a much better running time. Right? So what running time are we going to get here? So this is what we are trying to do is that if the rod is of length 0, then obviously we don't get any cost. Otherwise, we just set it to minus infinity. Okay? We could take any large negative value and keep on updating this Q. Okay. So for I from 1 to n, Q will be the maximum of Q comma Pi plus cut the rod into. This is the recursive call we are making P comma n minus I. Then finally we just return the subsequent value of Q. So what's the running time here?
Two raised to n.
2 raised to n. Yeah, that's correct. So we still need to do some more things, and again it's boiling down to exponential. Okay, so what do we do next? This approach also failed, and somehow want to bring this down to polynomial. Because the main problem is that this size is not going down by too much, just n minus I, whatever. So how do we get to polynomial right? And so we'll just look at what's exactly happening here. Okay? So initially we said that there is this length for rod. Let's assume the first cut was made. Okay. And then we reduced it to cut rod P3. Right? We decided to make a cut after length 1 and the total will be P1 plus R3, P2 plus R, P3 plus R1 and P4 plus R2. Okay? So we divided into various subproblems. Okay. And the thing is that again, this when we call this cut rod P3, it again divides into cut rod P2 and so on. Okay. This will again get divided into cut rod P1, cut rod P0, and so on. Okay. And the reason for this uh, running time is that you are again and again recomputing these solutions. Okay. After every recursive call. Okay. So a better idea is to store the solutions. Just compute them once and store the solutions. Okay. So this was the recurrence for the previous problem, which is Tn is 1 plus uh, Tj. In case you didn't figure it out here. Okay. So this part takes constant time, but there is this Tn minus I. And you want to sum up from I1 to n. Okay. So 1 plus summation Tj, where j goes from 1 to n minus 1. And if you solve this recurrence, you'll get 2 raised to n. Okay. So we are solving these subproblems again and again, and therefore, to compute the value of the optimal solutions, I'll present two different approaches, which is using an array. We store the values of the subproblems, then use those things. Okay. So let's consider our special case of n equal to 4. Initially, we create this array or table or dictionary or whatever, set this to minus infinity. Okay. Okay. So let me just. Okay. So we'll see these two approaches, which is top down with memoization and bottom up with tabulation. Okay. So this is our pseudocode. Let R be defined as a new array. For initially, we don't know what's the optimal revenue we will get. So set it to minus infinity. Okay. And then we just return this memoized cut. Okay. We define this new array. If Rn is greater than equal to 0, then return Rn. Okay. And let's define some variable q, which will store the value of the current revenue, okay, maximum revenue. So if the rod of length 0, then we get 0 revenue. Otherwise, we set to minus infinity, and it will be the maximum of q. And assuming that the first cut is made at I, that's our guess, and we try all possible guesses. So we loop from I from 1 to n. Okay. This is our memoized approach, p comma n minus I. Okay. And finally, we store, once we have calculated this, we will store the nth value in this array to be equal to q, and then use it again and again. So notice that each of these values, Ri, R0, once we have computed it, we store in this array. Similarly for R1, R2, and so on. Okay. And finally, we store the value of Rn by using this memoized approach. Okay. So there are totally big O of n subproblems because we need to find this R0, R1, R2, Rn minus 1. And each of these steps, there is just one for loop and we are just doing constant amount of work because this was already known to us, n minus I, whatever are the values. We just look at the corresponding value in the array and add and do some maximums. And so each of these subproblems will only take linear amount of time, big O of n, and we had big O of n subproblems, and therefore it's just big O of n squared. Okay. So this is a nice approach. So notice that why do we call this top down? It's because we started from the top. We wanted to compute Rn, and then we kept on reducing this value. Uh, use the solution of Rn minus I to compute Rn. So we start from the top and keep on reducing this value to get a better algorithm, better running time algorithm. Okay. So that is why it's called top down with memoization, because you are memorizing the value of which we have already computed and storing in some array. Okay. And once we have calculated this value, we don't have to compute it again and again. Okay. So each subproblem is executed only once. It solves subproblems of different sizes, and that's the way we do it. Right. Total running time will be I from 0 to n, big O of I. This is well known to you. Uh, just add numbers from 1 to n, big O of n squared. Okay. And in general, you have this, you can use this formula, which is you multiply the total number of subproblems by the time taken by a subproblem without recursive calls. Okay. But the only problem is how much extra space does it need? This array has n many elements, so it needs big O of n space. And somehow we want to reduce this extra space. It's too much linear space. Can we solve this problem in constant amount of space, extra space? Okay. So for that we have another approach, which is this bottom-up approach. Okay. So what's this thing? Initially we were going from top to down. For computing Rn, we needed Rn minus I and so on. Now we will start from bottom. Okay, so R0 is set to 0 because rod of length 0 will give you 0 revenue, and then keep on iterating this. For I from 1 to j, we will set, initially we set to minus infinity and then take the maximum of q and pi plus rj minus I. This means the first cut was at step I. Okay, so the first part has length I and then keep on recursively calling this. And then finally store the value of rj. Okay, so what's the benefit of this? So when we wanted to compute Rj, we only needed this particular values. R for I from 1 to j, Rj minus I. Okay. Then we can use it and just The rest of the values we don't need at the moment, so we just store those values. Okay? So that's how it improves upon the space criteria. Okay? So here is one example for I1, 2, 3, 4. These are the various prices. The various sub-problems for this. And, right? So this is the total revenue we have, which is either you cut it at P1 plus R naught, P1 plus R1, P2 plus R naught. And this is for length 3, this is for length 4. Right? You take the maximum of all of these. Okay? But you can't pick any sub-problem of your choice. Okay? What are the problems that might arise here? Is that, let's say we considered n equal to 4. Okay? So the solution of n equal to 4 depends on all possible smaller lengths of problems, which is n equal to 3, 2, 1, 0. Similarly, the solution to 3 depends on 2, 1, 0. Solution to 2 depends on 1, 0, and so on. Okay? So we draw an edge from I to j if the solution to I depends on the value of j. Okay? Now, if this directed graph contains cycles, okay, then we have a problem. For instance, we don't want a cycle from 4 to 3 to 2 and 2 goes back to 4. Because then what happens? For the solution of 4, we need the solution of 2. And for solution of 2, we need the solution of 4. And then it will get stuck in an infinite loop because both of them are waiting for each other's solutions. Okay? So this is one small drawback, is that you need to choose these sub-problems very carefully so that you don't get stuck in an infinite loop. Okay? Yeah, that is the only thing you need to be careful of, is that the sub-problem graph, it should be a directed acyclic graph. And with some minor modifications, so this particular thing just gave you the maximum revenue, right? We don't know which parts you should cut. So that also you can figure out via some small modifications. In step, this thing is that we had this algorithm R0 equal to 0, then we set Q2 minus infinity, if Q is less than Pi plus Rj minus I, then we set Q2 Pi plus Rj minus I. Okay. And this is the first cut. You will remember Sj equal to I. So we store the first cut for any length rod in this new array. Okay. And then you will know that you just access this array, look at the first cut, then look at Sj minus I. That's the point where you'll make the second cut, and so on. Okay. So you can easily modify this array to return the exact solution as well. Okay. So yeah, it's fairly straightforward, and can have this print cut rod solution, which is R comma S is the extended bottom of cut rod. So it will consist of two arrays, R and S. R is the total revenue which you are storing, and S will tell you where to make the required cuts. Okay. So we print Sn, that will tell you the first cut where you need to make, and then n gets dropped from n to n minus s. Okay. So for instance, let's say we have this maximum revenue, and S will tell you where to make that required cut. Okay. Okay. So any questions? Problem.
Sir, can you please explain how their bottom-up approach was more space efficient?
Bottom-up approach was more space efficient. Yeah, that we will see. So in certain problems it is not, certain problems it is. So the next problem we'll see that it will only require constant amount of space.
Okay, sir.
Even in this problem, let me show you how it is more space efficient. So what we did, this was our, what you say, for I from 1 to j. Yeah, this approach it's not, but I'll show you some other examples where it turns out to be space efficient. Classes. And just one thing regarding the exam. So actually we have decided to keep negative marking also. So initially I thought there won't be any negative marking, but there will be negative marking. But it's very less, like just 1/4 of the total number of marks. Okay. That is one correction I wanted to make. And yeah, if there are no other questions, all the best for your mid semester. We'll meet after the mid-sem. What does amortization mean in the context of analysis of algorithm? So, I mean, it's a tricky concept actually, amortize. So, mostly this course doesn't deal with amortized things. Mostly we'll just deal with the worst case things. But roughly the fair idea, rough idea is you have certain budget, okay, and in the average case, the algorithms runs fast, but the worst case might be bad. Okay, so that's what we mean by amortized things is that most of the time that algorithm is fast, but in certain cases it might take linear quadratic time. Okay. About paper pattern. Yeah, I already told it's going to be objective type. Yeah, do you want to know anything specific about it?
So, sir,
Yeah,
सर मल्टीपल चॉइस में पार्शियल मार्किंग होगी?
no, there is no partial mark.
Yes, sir.
Okay, so I guess we'll stop this meeting now.